Okay, lesson number 2 looks at solving second degree equations where the power of the trig function is 2, such as sine squared x minus 3 sine x equals 0. We can also solve these equations using identities, but we'll learn about that later on in the course. So the first part of this just looks and reviews the idea of factoring. Only instead of just factoring a quadratic that had a variable, you're now factoring a sine function or a cos function. So if we look, I'm going to jump straight into class example number 1. If we look at factoring 8 tan a plus 4, remember all the different ways that we can factor. We look for a greatest common factor. We look for a difference of squares. We look for a quadratic. So in here, always start off with your greatest common factor. Do I have a common factor in both terms? 4. So if I divide both terms by 4, what's 8 tan a divided by 4? 2. So I'd get 2 tan a plus. Good. So if I look at B, I have sine squared x minus 3 sine x. So sine squared x is the same as sine x squared, like that. Okay, so it's the sine function that's being squared. So what is common to each term? Sine x. Sine x. So if I remove a sine x, what would I be left with?
Sine x minus 3.
If you look at C, 4 sine squared x minus 1, what do you notice? It's a difference of squares. If you want, rewrite it like this, S for sine. So I have a difference of squares. How do I factor that difference of squares?
Isn't it 2 sine x minus 1 and 2 minus plus 1?
Yes. So 2 sine x minus 1, 2 sine x plus 1. Good. Okay, if I look at D, cosecant squared x minus 3 cosecant x minus 28. Think of it as c squared minus 3c minus 28. How would I factor that as a quadratic?
Cosecant x minus 7, cosecant x plus 4.
So it's factoring the quadratic, two numbers that multiply to negative 28 and add to negative 3. So then I replace my c's with cosecant x. Cosecant x minus 7, cosecant x plus 4. And then the last one, 2 cos squared x plus 7 cos x minus 4. I can think of it as 2c squared plus 7c minus 4. How could I factor this one? Can I use inspection on this one? Or a form of inspection? The only way I can get 2c squared is to multiply c by 2c. Now I have to get this negative 4. So there's a couple of ways I could get negative 4. I could go 4 times 1, and I could go 2 times 2. I just have to figure out which combination is going to give me 7 in the middle. If I choose 2 and 2, I'm going to get a 2 and a 4, or sorry, a 4 and a 2, which is not going to get me to a 7. So I'm going to have to use the 1 and the 4. I have to put the 4 opposite the 2, because that's going to give me 8. 1, there's my 7, if I find the difference between them. So a positive 8 and a negative 1. Change this back, I get 2 cos x minus 1 and cos x plus 4. So what I want you to do is question number 1, which is factoring these trig functions. It's important because without being able to factor these trig functions, you're not going to be able to solve these trig equations. Okay. So in continuing with lesson number 2, solving a second degree trig function, we started the other day with the factoring of trig functions. The idea that we can treat a trig function the same as we do our polynomials and we can factor it. And that becomes important when we're trying to solve them. So if we look at class example number 2, it says consider the equation 2 sine squared x equals 1 minus sine x. It says use a graphical approach to determine the roots of the equation where x is between 0 and 2 pi and give the solutions as exact multiples of pi. So what I'd like you to do is work on that for a couple of minutes using your graphing calculators. Okay, so here are my 2 graphs that I get on my calculator screen. And what I'm looking for is I'm looking for intersection points here, here, and here. So what was this intersection point?
Pi over 6.
Pi over 6. So then x would equal pi over 6. The next one?
5 pi over 6.
And the last one?
3 pi over 2.
3 pi over 2. Okay? If I was to convert this to general solutions, what is the period of this function? So we look at the periods of sine x. The period of sine x is 2 pi. So it's taking each of these solutions and adding a multiple of 2 pi. And again, n is an integer. And the other thing that I do when I'm looking at the general solution is I just take a moment to quickly look and make sure that there's no way of going from pi over 6 to 5 pi over 6 to the next whatever pi over 6 it would be, and there isn't. And the same thing with 3 pi over 2. The next solution that's going to come is going to be down here in the next period. Okay? So now if I look at this algebraically, what we would do is we would treat this as a polynomial. If you find it easier to get rid of the idea of it being sine and just use a letter for sine instead, you could rewrite this as 2s squared equals 1 minus s. So if I gave that to you as a quadratic, how would you go about solving it? What would you do first?
1 minus s to the other side.
Bring everything to one side. So 2s squared plus s minus 1 equals 0. That's step 1. What's step 2? Factor it out. So how would I factor this out? Can I factor it kind of using that inspection type method? Yeah, because 2 is a prime number. The only way I'm going to get 2s squared is to take 2s and multiply it by s. And the only way I'm going to get a negative 1 is to do what? So I'm going to have a 1 and a 1. 1 has to be positive, 1 has to be negative. How do I know which one is negative? The one with the 2s or the one with just the s? The one with the 2s? Because then I get a negative s and a positive 2s, which together gives me my positive. Now that I have this factored, stick the sign back in there. 2 sine x minus 1 and sine x plus 1. Now if we go back to our zero theorem that we looked at in polynomials, it basically says if either one of these factors were to equal 0, the whole thing equals 0. So what I can do is I can let 2 sine x minus 1 equals 0 and sine x plus 1 equals 0 and solve each of those factors separately. would isolate sine x, and I would get sine x equals 1/2, and then I go through those algebraic steps that I've done in the past. So the first thing I do, figure out what quadrant would sine x be in. So what quadrants is sine positive? 1 and 2. And then determine what is my reference angle. So what do you get for a reference angle? Pi over 6. So in quadrant 1, x is equal to pi over 6. And in quadrant 2, x would be equal to the 5 pi over 6, because it would be the 2 pi, or sorry, not 2 pi, pi minus pi over 6 in quadrant 2. And then if I look at the next factor, sine x plus 1 equals 0. Again, I isolate sine x, and I get sine x equals -1. So what quadrants is sine negative?
3 and 4.
So then I find my reference angle. What's my reference angle, Jessica?
Pi over 2.
Pi over 2. So then if I'm in quadrant 3, x would be equal to pi plus pi over 2, which is 3 pi over 2. And if I'm in quadrant 4, it's 2 pi minus pi over 2, which is still 3 pi over 2. So that's how I would get my solutions algebraically. And then the general solution again, I would take these values and add one period of the cycle. So pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, and 3 pi over 2 plus 2 pi n. Again, making sure that n is an integer. Okay, so now what we're going to do is we're going to use an algebraic procedure to determine the roots of the equation on the given domain and also state the general solution. So I'll get you started on A. I have 4 sine squared A minus 1. So again, if I did that substitution and rewrote it as 4s squared minus 1 equals 0, what kind of a polynomial do I have here?
Difference of squares.
I have a difference of squares. So factor the difference of squares and then work through the rest of the question. So I'll give you a couple of minutes to do that. So if I look at this 4s squared minus 1, when I factor it, what do I get? And those s's were signs, so now I can replace it, and I get 2 sine x plus 1 and 2 sine x minus 1. And then I let each of those factors be equal to 0, and then we go ahead and solve them. So with the 2 sine x plus 1, I would have to isolate sine x. So sine x equals -1/2. Okay, so how do I proceed from this point?
Determine the quadrants it's in.
Which quadrants are it?
3.
Okay. Reference angle is?
Pi over 6.
So in quadrant 3, what's my solution?
7 pi over 6.
And in quadrant 4, it would be then when we look at the next one, we've got sine x would equal positive 1/2, which now puts us in quadrants 1 and 2. Same reference angle. So in quadrant 1, what would x equal?
Pi over 6.
And in quadrant 2?
5 pi over 6.
So now if I wanted to come up with a general solution, what would my general solution be?
Pi over 6 plus pi n. And 5 pi over 6 plus pi.
It's not 2 pi. So why pi over n and not 2 pi?
Because when you add a whole pi, then you'll get the next.
Yeah, if I add pi, I end up with 7 pi. Okay? Would it be correct to still go pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6? Yes, it would still be correct, but it's kind of repetitive. And if it was in the form of a multiple choice question, this would most likely be the answer that you would see, because that is the simplest general solution to come up with. Okay? Okay, so let's take a look at B. How did you approach this one?
I factored out a tan x.
And what did that leave you with?
Tan x plus 1.
Okay, then what?
And I made both sides equal 0, so tan x equals 0. And tan x plus 1 equals 0.
Okay. So if tan x equals 0, what quadrants am I looking at?
All of them.
You're looking at all 4. What's my reference angle when tan x equals 0?
0.
So in quadrant 1, that would be 0. In quadrant 2, it would be pi minus the reference angle, which would be pi. Quadrant 3 is pi plus the reference angle, so it would be pi again. And then quadrant 4 is 2 pi minus the reference angle. So there's my solutions. Now if I go to this one, I let tan x equal -1. What quadrants am I in?
2 and 4.
What's my reference angle?
Pi over 4.
So in quadrant 2, what would that be?
3 pi over 4.
3 pi over 4, because it would be pi minus this. And in quadrant 4,
7 pi over 4.
so there are my solutions from 0 to 2 pi. Then my general solution wouldn't really start with 0, I'd start with pi. What multiples would I add?
Pi n.
Pi n. And I would start with pi n simply because that's the period of tan. And then check, if I add pi, do I get to the next solution? Yes. 3 pi over 4. If I add a multiple of pi, do I get to 7 pi over 4? Yes. So there's my general solution. Okay? The last two questions, or sorry, the last two questions just change this from an equation to a function, which in a sense really means the same thing. We're going to let f of x equals 0 and we're going to solve. A is a little bit more complicated because we're dealing with a reciprocal trig function. But we're still going to start off treating it the same way. So if I look at this as c squared minus 3c minus 28, and I let it be equal to 0, how can I factor that? two numbers that multiply to negative 28 and add to negative 3.
-7.
So then I have cosecant x minus 7 and cosecant x plus 4. So then I've got cosecant x equals 7 and cosecant x equals negative 4. If I isolate for cosecant. What is cosecant the reciprocal of? Sine. So if cosecant x equals 7, it means that sine x would equal 1 over 7. And instead of cosecant x equaling negative 4, sine x would now equal negative 1/4. Okay, so now I'm going to give you a couple of minutes to finish this. You're determining the zeros. Look at the domain. So what quadrants are you dealing with? 1 and 2. Okay, so you're only dealing with the first two quadrants, and you're in degree mode. Okay, so if we look at sine x equals 1 over 7, what quadrants would that put me in? 1 and 2, which fits within the given domain. So now I find my reference angle. What is my reference angle? To the nearest degree. What did you get for a reference angle, Hannah? 8 degrees. So in quadrant 1, x would equal, and in quadrant 2, what would it equal?
172.
Okay. Now if I look at sine x equals negative 1/4, what quadrants does that put me in?
3 and 4.
Quadrants 3 and 4. Is that within my domain? So I stop. It's not in the domain. I don't need to go any further. Okay, so now let's look at G. I'll give you a couple of minutes to factor it, and then we'll check to see if the factoring is done correctly, and then we'll continue on. So if I go to factor this, in order to get the 2 cos squared, I know I have to have 2 cos theta this time, not x, and cos theta. To get the 3, it's going to have to be 3 and 1. But to get this 5 in the middle, I'll need to make this a positive 3 to get my positive 6, and then my negative 1. So now when I go through, are we past this point? So 2 cos x minus 1, if I let that equal 0 and isolate, I get cos theta equals 1/2. What quadrants would I be in?
Only in quadrant 4 because of the domain.
Well, I'm from negative pi to positive pi. So negative pi is here, and positive pi is there. So it's still looking, I still have the quadrants to think about. But what I'm going to look at is, we're going to look entirely at our reference angle and not necessarily think about our quadrants yet. So what would my reference angle be? Pi over 3. So if I think of this in terms of a sketch, and I know that I still have to be kind of within quadrants 1 and 4 in order to have a positive cosine, then when I'm from negative pi, which is here, to positive pi, which is there, do I still pass through this quadrant? Do I still pass through quadrant 4? I do. Only only this time, instead of going from here to there, I'm going backwards. So I would end up with a negative pi over 4. Or sorry, negative pi over 3. That's what it would look like in quadrant 4 because of where my domain is. And then in quadrant 1, I have my pi over 3, which is between 0 and pi. So my two solutions would be that theta can equal pi over 3 and negative pi over 3. Now if I look at the other factor, I get cos theta equals negative 3. And we talked about this the other day. Can cos ever be greater than 1? No, because it's something over the hypotenuse. So at this point, there is no solution for this factor.